Okay, so I believe we can get started. So good afternoon. Today's speaker is Professor Pavel Kovtun. Oops. Okay, this was some comment from Kobe, excuse me. So today's speaker is Professor Pavel Kovtun from the University of Victoria. So Professor Kovtun did his undergraduate degree in Kharkiv, Ukraine. And for a theoretical physicist like me, the name Kharkiv reminds me of Lev Landau, since he spent an early part of his career there, I understand. Indeed, Professor Kovtun told me that he grew up literally next door to the Physics Institute where Landau worked. And he thought that physics is what most people do for a living. So he then came to the United States and received his PhD from the University of Washington, Seattle in 2004. So I understand his advisor was Larry Yahe. And in fact, Larry Yahe did his undergraduate study at Caltech. Professor Kovtun then was a postdoctoral fellow at the Cabri Institute for Theoretical Physics, Santa Barbara, before joining the University of Victoria in 2007, where he is now an associate professor. Professor Kovtun has worked on quantum and statistical field theory and applied string theory. Among his many achievements is the discovery of the universal property of the viscosity and strongly interacting quantum fluid through the connection between fluid mechanics and black hole physics. For example, he and his collaborator used string theory and the holographic principle to predict a novel phase of matter with extreme low viscosity, where the ratio of the shear viscosity coefficient and entropy density is equal to the ratio of Planck constant and the Boltzmann constant divided by 4 pi, which is about 6 times 10 to the minus 13 Kelvin second. More recently, he has been interested in foundational questions in the hydrodynamics and relativistic fluid, I think some of which he is going to tell us today. The title of his talk today is Pushing the Limit of Hydrodynamics. Professor Kovtun can take questions from the audience during the talk, as well as at the Q&A session after the talk. If you have questions, please raise your blue hand during one of the using one of the Zoom features, and wait for me to call you, and I will then allow you unmute yourself so that you can ask questions. So please join me to welcome Professor Kovtun.
Thank you. Thank you, Hiroshi, for the kind introduction, and thank you for the invitation to come, quote unquote, virtually and to speak, share some of my thoughts on the subject of fluid dynamics. So I'll be talking about hydrodynamics, which of course is an established field. It has a venerable history, many applications. However, today I will not talk about applications. Rather, I would like to highlight some foundational questions that came to light in the last few years. So here's a better title for my talk. It's a theoretical physicist's perspective. So what is hydrodynamics? It is basically a set of equations that tell you how stuff flows. So what is stuff? Stuff can be water, can be air, could be a cold atomic cloud, could be hot primordial matter in early universe, could be an electron fluid, etc. So let's say you are a student and you want to study fluid mechanics. And as a student, I remember my own times, you open a book that says hydrodynamics or fluid mechanics on the book cover, and you would often see derivations, approximations, applications, and all of that will be mixed together. So if as a student, you're also learning about vector calculus and partial differential equations at the same time, it can be hard to see the big picture. But the big picture of hydrodynamics is in fact quite simple. So here it is. Hydrodynamics is essentially a macroscopic theory of things that cannot disappear. So in other words, things that are conserved. So the way we write conservation laws in physics when we teach different classes is like this. In the left-hand side, we have the time derivative of some conserved density. And in the right-hand side, we have minus the divergence of the flux vector of that same conserved density. So we write down this equation, say, when we talk about the conservation of charge in electrodynamics, in which case rho A is the density of charge. We write down this equation when we talk about quantum mechanics, in which case rho A is the density of probability, the absolute value squared of the wave function. We write down this equation when we talk about conservation of mass in fluid mechanics. The equation looks exactly the same. That's a generic form of a conservation law. So another ingredient that you need for fluid mechanics is what people call constitutive relations. So how does this work? So our conservation law looks like this. It's one equation. And if you look at the functions that you have in the equations, you have 4 functions if you are in 3 dimensions, right? So rho is one function and flux has 3 components. It's a vector with 3 components. So total 4. And you have 1 equations, 4 functions, not much you can do with this. Now, the biggest assumption that fluid mechanics makes is that you assume that the flux is a function of the conserved density. Then you take this expression, which people call the constitutive relation, you stick it back into the conservation law, and then you only have the equation for the density, which you can solve. So more generally, it will be useful in practice or sometimes mandated by the microscopic symmetry principles, not just to use the density, but to use what I will call useful quantities, gamma, such as temperature or the fluid velocity, so on, and express both the density and the flux as functions of that useful quantity. And then you have equations for those useful quantities, which we can solve. So let me give you an example, a simple example of how that would work. So let's say my density is the density of energy, and my useful quantity, gamma, is the temperature. Then in the left-hand side of the conservation law, I have the density of energy as a function of temperature. We write this down through the equation of state, energy density as a function of temperature. In the right-hand side, I have the energy flux. Now, energy flux is a vector. Temperature is a scalar. What is the simplest way to make a vector out of a scalar? Well, you take the gradient. So you stick out some constant out in front, kappa, that is the heat conductivity, and you write the energy flux proportional to the gradient of temperature. Then it's quite easy to see that once you take this E of t, stick it into the left-hand side of the conservation law, and take this flux in the right-hand side, you will get the diffusion equation for fluctuations of temperature. So you have 1 time derivative in the left-hand side, and you have 2 space derivatives in the right-hand side, 1 space derivative from this gradient, another space derivative from here. Okay, so this is how the diffusion equation arises in fluid mechanics. So here is the summary. You have conservation laws, and you have constitutive relations. And as we have seen, in general, the constitutive relations can involve gradients of those useful quantities, as, for example, on the previous slide we had for the flux. So this procedure of combining conservation laws and constitutive relations is exactly the same whether the fundamental constitutes a quantum or classical, relativistic or not. You have normal fluid, a superfluid, you have magnetic fields, maybe you have magnetohydrodynamics, you have chiral fluid, not chiral fluid. All of that works exactly the same. The fundamental principle is the same. Now, you can do various simplifications. For example, if you by hand just throw away all the terms in those constitutive relations that involve the gradients of your useful quantities, you get what people call perfect fluids. The conservation laws are in this case called the Euler equations of hydrodynamics. If by hand you throw away all the terms that have 2 and more derivatives of the useful quantities, you get what people call viscous fluids, in which case the conservation laws are the Navistox equations of hydrodynamics. You can throw away less, in which case you have 2nd order fluids or Burnett equations, and so on. Now, so this was the summary. Hydrodynamics is our model of macroscopic phenomena. And we know as physicists that every theory in physics is wrong. More precisely, it's only approximately correct, limited by its domain of applicability. And whenever we write down any equations that attempt to describe physical phenomena, we have to answer these questions. Do these equations even make physical sense? Can you improve the equations to capture more physics? And what kind of physics is beyond our equations? So what will follow are 3 short stories, 1 story for each question. So this is the plan of the talk, to give some comments on these 3 questions. So my first question is, do hydrodynamic equations even make sense? So you might think it's strange question to ask. After all, hydrodynamics has been around for over 100 years. Well, still, let's look at this in more detail. So I want to talk about relativistic things. So let's say you are a student in subatomic physics or in astrophysics, and you want to learn about relativistic Navier-Stokes equations. So maybe you want to study the quark-gluon plasma produced in nuclear collisions. Or maybe you want to see the effects of viscosity during neutron star mergers. So as a student, you might be tempted to learn about relativistic fluid mechanics from classic textbooks. And I still remember those days when people used books, when libraries had books and you would go like find one. Oh, wow, great. So libraries had stuff that is more than computer terminals. And, I came from the Soviet School of Physics, where there was a certain kind of Bible that every student was subject to. That Bible was a 10-volume Bible called The Course of Theoretical Physics of Landau and Lifshitz. And volume 6 of that Bible was fluid mechanics. So you can open volume 6, and there are some relativistic hydrodynamic equations, some relativistic Navier-Stokes equations. And you think, okay, fine. So then I came to the West, and I realized that in the West, people may have other Bibles. That is not Landau-Lifshitz. So as a student, I had a copy of Gravitation and Cosmology by Weinberg. And you can open Weinberg. And also there is a section about relativistic Navier-Stokes equations. This is actually a formulation due to Eckert from 1940. And you see some equations. And then you compare what you see in Landau-Lifshitz to what you see in Weinberg. And these equations actually look very different. So as a student, you're probably confused. So which ones are correct? But then as a student, you're often taught to shut up and calculate. Okay, let's shut up and equilibrium, no external field equilibrium that you study in thermal physics, and you study linearized perturbations of the thermal equilibrium state. Then you will see that both Landau-Lifshitz and Eckert's equations, they predict 2 things. 1, they predict that thermal equilibrium does not exist. And 2, they predict that things propagate faster than light. Okay. So I put down some reference here to Hiscock and Lindblom in the 80s, but people have known about that from before then. So it's actually quite embarrassing. Okay. So it's sad but true. The equations you find in the classic textbooks, they make no physical sense. And this has led to the belief that the Navier-Stokes equations cannot be unified with Einstein's relativity, and that they have to be abandoned in a relativistic setting. Other exotic theories have been proposed in the 1970s to replace the Navier-Stokes, and the field has moved on. But as a student, you still have this question. So why do the theories of Landau, Lifshitz, and Eckert, why do they differ in the first place? Why? So to understand why, let's first talk about temperature. So I'll give you a minute to read the cartoon, the XKCD cartoon here. Okay, so temperature is subtle. As we teach our students in statistical physics, temperature is something that you would measure by using a thermometer. So let's talk about thermometers for a little bit. So by definition, of course, temperature is what you measure by thermometer in equilibrium. So what I have on the left is two identical boxes of my stuff. So the stuff is represented by this, yellow color, and I have two different thermometers that are immersed in my stuff. Thermometer is a little heat bath connected to a gauge. So they have two little thermometers, the green one and the red one. They're connected to their gauges. And in identical equilibrium states, these two different but properly calibrated thermometers will show the same temperature. Now, let's take the same two thermometers and stick them in identical non-equilibrium states. Now, in identical non-equilibrium states, the same two thermometers will show different temperatures, even though they show the same temperature in equilibrium. So why is this so? Well, we know this if we have two different thermometers outside our window, say the temperature drops or rises very quickly. One of the thermometers may not have enough time to react to temperature changes. So it will take longer for that thermometer to adjust. Or maybe there are some gradients, spatial gradients of energy outside, and the shape of these blobs would be different. So the differences are subtle. But if you want to understand things like viscosity and viscous equations, it is those differences that will be important. So there is some arbitrariness in what you mean by fluid temperature out of equilibrium. And that is because our choice of a thermometer is essentially a convention of how we choose to define out of equilibrium temperature. There is also the same arbitrariness in what you mean by the fluid velocity. And that is because our choice of a velocimeter is a convention. And so what happens is that Landau-Lifshitz version of Navier-Stokes equations uses one convention. Eckart's version of Navier-Stokes uses a different convention. And if you think about this for a minute, then you will realize there is simply no such thing as quote unquote the Navier-Stokes equation until you specify early. Now, it's very important that different conventions give rise to different mathematically inequivalent Navier-Stokes equations. So that's not a typo, inequivalent. So the conventions have real physical consequences. Now, why is this? Well, this is because the Navier-Stokes equations only give you a crude approximation of the real fluid. The difference between the conventions is hidden in the crudeness of that approximation. But the crudeness of the approximation is enough to change the mathematical structure of the equations. Landau, Lifshitz, and Eckert, they adopt different conventions for Navier-Stokes, but both of those conventions are bad, and both lead to nonsensical predictions. So what exactly is wrong with the classics? So you can understand this. You can understand it quite easily. So both Landau, Lifshitz, and Eckert, they define temperature using this expression as written on this slide. They say the exact non-equilibrium density of energy is equal to epsilon of T, which is the function given by the equation of state. Now remember, energy is the real thing. Temperature is just a proxy for energy. But for symmetry reasons, it's temperature that is used in Navier-Stokes, not energy. So if you define your temperature by this equation on the slide, what this means the following. As the local energy density changes, the thermometer reacts instantaneously. It's just like that. So the temperature changes instantaneously. So such thermometers, they turn out to violate relativity, and they lead to superluminal propagation in relativistic fluid dynamics. Well, you can ask, okay, so if it is that simple, why don't you choose a thermometer or velocimeter that does not react instantaneously and respects relativity? So in other words, can you just adopt a sensible convention? And the answer is, well, yes, you can. With good conventions that you can adopt, the equilibrium is stable, signals propagate slower than light, the equations are mathematically well posed, and they can be coupled to Einstein's gravity. So people have started to play with this only last year. And now we just need to make some more progress in terms of the numerical approach. So the bottom line is this. Unifying Navier-Stokes with relativity was thought to be impossible for many decades. But if you choose a sensible thermometer or velocimeter, then the Navier-Stokes equations are happily unified with relativity. And basically now what you need to do, you need to develop numerical codes and apply them to physical systems. But there's also a question. And the question is this. What I told you is that in order to make relativistic Navier-Stokes equations well-defined, sensible, you need to make a clever choice of temperature and the velocity. And this means that the parameters of your thermometers or velocimeters or whatnot will appear in your equations. And this is actually seems to be the case with every single formulation of relativistic Navier-Stokes equations. The relativistic Navier-Stokes equations, in order to make them sensible, no matter what you do, they seem to require that extra non-hydrodynamic parameters must appear in the equations. It's like if you're familiar with field theory, it's like in order to make field theory well-defined, you need to formulate it with a cutoff, with an ultraviolet cutoff. Now, in hydrodynamics, it's the same. But what this means that the solutions of your equations will now contain those non-hydrodynamic parameters. So if the solutions contain these parameters that are not universal, does your hydrodynamics actually have predictive power? Can you do hydrodynamics in the same way as you do field theory, in a way that the low energy predictions are independent of the UV cutoff, of the short distance cutoff? It's not clear to me that it's possible to do so. And if you have thoughts or comments on that question, I would be very happy to hear and very happy to discuss. So with that, let me move on to my second story. And the second story is this: other limits to improving the equations of hydrodynamics. So let's take a first look at the limitations. So what I have here is a cartoon of some microscopic constituents of matter represented by these blobs. And there's some typical microscopic distance scale that is represented by a little L here. And the second plot here is a picture of a solution to Navier-Stokes equations. So this would show you how, for example, temperature or the velocity or the density, how they change with distance. And in your solutions, there will also be a typical distance scale that I call capital L here. So this is the distance scale of the solution that comes out of your equation. And you may think that hydrodynamics is probably reliable. It's probably okay if this distance scale, capital L, is much bigger than the small l, which kind of makes sense. So on the other hand, if you solve your equation and you find a solution where, say, the fluid velocity or temperature, they change very rapidly like this, so the distance scale of the variation of your solution is comparable to the microscopic distance scale, then you maybe think, well, you should not trust a solution like that. Okay, so hydrodynamics is probably not okay when the derivatives are large. So what this motivates a way to think about fluid dynamics as an expansion in derivatives. So I said that there are conservation laws and the constitutive relations. So conservation laws, they're always true. They don't care about what we do with small derivatives, large derivatives. But the constitutive relations, they are sensitive to whether the derivatives are small or large. And so what I'm doing here, I'm organizing my constitutive relations as an expansion in derivatives. So something with superscript 0 has no derivatives of my useful quantities, such as temperature, velocity, whatnot. Something with one derivative has something with superscript 1 has one derivative of my useful quantities. Superscript 2 has two derivatives, and so on. Now, if you only look at these terms, this is what you call perfect fluids. Of course, perfect fluid is the most imperfect model of a fluid. They cannot flow through a pipe. Sound propagates forever. Diffusion does not exist. If you look at the first terms, this is the Navistox fluid. It's an improvement of the imperfect perfect fluid. You introduce dissipation and restore common sense. These are the second order fluids, which would be an improvement of the Navier-Stokes fluids, etc. Well, let's ask this question. Can you keep improving forever? Let's say you generate an infinite series in these derivatives. Does the series converge? As for example, in this series, when you sum 1 over n squared, you get pi squared over 6, a finite number. Or does the series diverge? That is, when you sum 1 over n, you get an infinity. So is the series of hydrodynamics like that or like that? So if the series converges, then your theory can be systematically improved to include more and more transport phenomena. And if it diverges, then there are more questions than answers. Then hydrodynamics is not really supposed to work, but it seems to work in practice. Why? So is hydrodynamics a fluke, or are there other phenomena that happen macroscopically that maybe we don't understand? So how to answer this question about convergence? And what exactly is the expansion? Because you see, when I sum 1 over n squared, it's clear what the series is. And when I write down a series like this is very abstract. It's not even clear how to sum, the series. There are many terms at each order, in the expansion here. Again, I want to look at the simplest possible example. Let's just take a plane wave and look at infinitesimal perturbations of equilibrium. And when you look at a plane wave, then the derivative, when it acts on the plane wave, it brings you I times k, where k is the wave vector that sits in the plane wave. So the hydrodynamic expansion is really an expansion in powers of k. So what is expanded in powers of k? Of course, as we teach our students in elementary physics, when you take a plane wave and stick it into whatever equations you want, you get so-called dispersion relations. You get the relationship between the frequency and the wavelength, or the frequency and the wave vector. Same in hydrodynamics, the frequency and the wave vector will be related by the dispersion relations. So for example, here, the frequency of the sound wave will be related to the wave vector like this. It will be given by a power series in k. So the first term is, of course, what we know from first year physics. It's plus minus speed of sound. Vs is the speed of sound times k. This is normal perfect waves. Then there is a second term here with k squared that comes from Navier-Stokes. It comes with an I because it describes dissipation, and this coefficient gamma is proportional to the viscosity of the fluid. And then there is dot, dot, dot. There are more of those. So you can ask the question, do the series like that, do they converge or diverge in hydrodynamics? How do you do this? Well, you just calculate all those coefficients, A, B, C, D, and so on. And then you ask yourself, well, how do you do this? Well, let's take, you have like, a near ideal gas, and you try to calculate this. Okay, so this is maybe given by the equation, comes from the equation of state. So you know the equation of state, but this B, C, and D, I mean, these are quite hard to calculate, even when you have, things like the Boltzmann equation, or even if we have quantum field theory with very, very small interaction. Calculating these numbers is a very challenging task. So you don't necessarily know how to answer the question about this, about calculating all of these coefficients in generality. So basically, you have to look at examples. So let me also do the same, but let me look at an example that is not the Boltzmann equation, sort of an example from the opposite limit. So there are fluids that can be studied analytically using the tools of the so-called holography. So if you don't know what holography is, don't worry about it. Basically, holography is a mathematical method that allows you to solve for, allows you to understand certain kinds of fluids that are morally speaking similar to the quark-gluon plasma produced in nuclear collisions. fluids that are made out of gluons and other things that are similar to quarks. Okay, and these methods of holography allow you to do many things exactly. So in the simplest solvable examples of those fluids that you can study using these methods, we did this. We found that the sound wave as a function of the wave vector is given by an analytic function of k convergent for some in some finite domain when k is less than the critical value. Some nice universal numbers here. The critical value determined by the Boltzmann constants, h bar, speed of light, the temperature, and whatnot. So the convergence in those examples that are similar to the quark gluon plasma, it gives you hope that hydrodynamics is in fact improvable. But I don't want to talk about this convergence per se. I want to talk why there is a critical value there, because there's some physics hidden in there. And to understand why there is a critical value in the convergence of the derivative expansion, let's look at this example from basic math. So let's look at a function f of x is equal to 1 divided by 1 plus x squared. So this function is plotted here on the left, and it's a perfectly smooth function for all real x from -infinity to infinity. Let us try to expand this function as a Taylor series about x is equal to 0. You construct the Taylor series, and then you realize that the Taylor series only converges when absolute value of x is less than 1. So why does the Taylor series only converge when the absolute value of x is less than 1? X is equal to 1 is here. There are no singularities in this function. The function is perfectly smooth. All the derivatives exist. Now, to understand why it only converges when x is less than 1, you need to take x complex. When you take x complex, then you realize that this function, when x is complex, it has singularities at x is equal to plus minus I. And in the plane of complex x, when you draw a circle whose radius is the distance to the nearest singularity, the radius of that circle is 1. So this number 1 in the right-hand side, when x is less than 1, is actually the absolute value of I. Okay. So similarly, what happens with these dispersion relations is that frequency is a smooth function of the real wave vector. And to understand why it is only convergent within some finite domain, you must take the wave vector complex. So let's talk about the complex frequency and the complex wave vector. In classical physics, dispersion relations such as this, omega is a function of k, they came about by solving some equation, some function of omega and k squared is equal to 0, where this function f is determined by the equations that you want to solve. This could be hydrodynamic equations, they could be Maxwell's equations in matter, whatnot. For example, in the example of diffusion that I talked about earlier, your equation is like this: 1 time derivative, 2 space derivatives. And if you apply this to plane wave, you see that 1 time derivative gives you minus I times omega. 2 space derivatives gives you a factor of k squared when you apply this to the plane wave. And so this is your capital F. That's what it looks like. If you want to study sound waves, then this function happens to look slightly more complicated, but not much more. It has omega squared and k squared. Vs is the speed of sound. And it has some term that has an I and some coefficient gamma that is proportional to the viscosity of the fluid. All right. So, so these are equations like this that we need to solve. So when we teach about waves and dissipation in our undergraduate classes, we usually tell our students one of two things. We say, OK, we have an equation like this. And let's take omega to be a real number. And then you will realize that it is only possible to solve this equation when k as a function of omega is complex. The imaginary part of k is then interpreted as the damping length or the penetration depth for the wave as it propagates inside your material. Another thing that we tell our students, we say, oh, let's take k real. Then, in order to be able to solve this equation, you will find omega of k, and this omega now turns out to be complex. And then the imaginary part of omega you will interpret as the relaxation time. Now, what if both omega and k are complex? This is not something we usually teach our students. Okay, so let me look at what happens when both are complex. So what you're looking at here, you're looking at a picture of oscillation modes of a certain kind of fluid. So these are the kinds of fluid that you can study analytically, again, using those methods of holography. And what you're looking at the plane of complex frequency. Real part of frequency on the horizontal axis, imaginary part of frequency on the vertical axis. My frequency here is measured in units of temperature. You see h bar omega divided by kT. Kb is the Boltzmann's constant. And this plot is made for us at a certain value of the wave vector. So Q is my wave vector measured in units of temperature. There is also, you see, there is also a speed of light here. That's because the fluid is, more or less speaking, it's like similar to the black body radiation, which is a relativistic system. Of course, black body radiation, you always have h bar times c, so that's why you have a c here. But basically, Q is the wave vector in units of temperature. So each dot in this plane corresponds to a solution to, f is equal to 0 for that fluid in the plane of complex frequency. So each dot here is basically an oscillation mode of your fluid. These two dots that are closest to the origin are the sound waves. The sound waves, they have this dispersion relation, as I said earlier. The second part with k squared comes because of the dissipation. So the dissipation becomes small when k is small. And remember, k is inversely proportional to the wavelengths. So the dissipation is small when the wavelength is large. This means that long wavelength waves, they propagate for longer distances than short wavelength waves. And as you take k to 0, meaning the limit of very, very long wavelengths, these two dots, the golden one and the green and the blue one, they will approach the origin. Now, the other dots, they're microscopic oscillation modes. They have no classical interpretation. They have nothing to do with fluid dynamics. They stay away from the origin as you take the limit of long wavelengths.
Do color means anything? The color of
Second?
So you have color coded these dots. What?
Yes, the color code. Yeah, the color coding does not mean anything in this picture. It will start meaning something, in the next slide. So at this point, the color coding does not do anything. Yeah.
So these dots are places for particular value of K, complex K.
Right. So in this case, the K is real. K is real, and K squared is real number. So it's equal to 1 in units of temperature. At this point, K is not complex yet.
Okay. Excuse me. Yeah. Thank you.
Yes. At this point, K is not complex yet. So here K is real. Frequency is complex. This is what these dots are in the plane of complex frequency. These are the complex values of frequency at a real value of K. Now what I want to do, I want to take K to be complex. So more precisely here, I will take K squared to be complex. So the picture that you're looking at here is still at real K. What I'm going to do now, I'm going to give my K squared a phase, and the phase is going to change from 0 to 2 pi. And as the phase of K squared changes from 0 to 2 pi, these dots are going to start to move in the plane of complex frequency. Okay, so this picture is K is the phase is equal to 0. Now the phase increases, and that picture is when the phase is equal to 2 pi. Okay, so the whole picture has to come back to itself. So if all the dots were black, the whole set of black dots would come back to the set of black dots when the angle is equal to 2 pi, because you're back to the same real number of the wave vector. So what you see has happened is that the blue and the one, so maybe I can show the picture again. So this is phase is equal to 0. Now you change the phase. Now the phase is equal to 2 pi. The blue and the gold, they swap places. And it's easier to understand why they swap places because I'm changing the phase of k squared here, not the phase of k. But they still remain sound modes. So in other words, if I take this picture now, and if I take the limit of long wavelengths, the blue and the gold dots, they will still approach the origin. And all the other ones, they will still remain away from the origin. They will still be the non-classical modes. Now, the next picture I want to show you is the picture when the wave vector is equal to q, or q squared is equal to 1.99 in units of temperature. So the picture you're looking at now is the wave vector is real. Now I'm going to change the phase. As the phase changes, these dots move in the plane of complex frequency. And here they are when the phase is equal to 2 pi. So this picture when the phase is equal to 2 pi. So you see that the sound modes, the blue one and the gold one, they still swap places, but they remain sound modes. In other words, now if I take the wave vector to 0, they again will approach the origin. They will be given by this perturbative expansion in powers of the wave vector. Now, the last picture I want to show you. So this picture is for the wave vector 1.99 in units of temperature. Next picture is when the wave vector is 2.01 in units of temperature. Now, what you're looking at now, the phase is equal to 0. Now I'm going to change the phase. And they move. And that picture is the phase is equal to 2 pi. Now, okay, if all of them are black, you look at the set of black dots, it comes back to the set of black dots, as it should. But now you see that one of the sound modes, the gold one, it now ended up here. So it now became a non-classical mode. Now, if you take the wave vector to 0, long wavelengths, it's the blue and the green that will approach the origin. But remember, the green was not the sound wave. It was a non-classical wave. But now it becomes a classical wave. Okay. So these pictures right here that is the same information as you saw in the videos on the previous slide. So the lines here, they trace the trajectories that are followed by the modes as the phase changes from 0 to 2 pi. So it's the same information as in the movies. It just shows the paths that are traced out by those dots. When the wave vector 1.99 in my units and when it is equal to 2.01 in my units. So what happens when you go from 1.99 to 2.01? Something changes. So what changes here, of course, the topology of the trajectories changes. What changes here, what happens is the collision of these modes, the collision of singularities. So at q squared is equal to 2, the modes collide, the topology of the trajectories changes. So the phenomenon you're looking at here is level crossing. But it's not level crossing in quantum mechanics, as many people are perhaps familiar with. This is level crossing in a macroscopic dissipative system. And the level crossing happens when a classical hydrodynamic excitations becomes a non-classical excitation. So classical excitation is something that you can easily describe by some partial differential equations of hydrodynamics. And non-classical excitations, it's really very short distance microscopic physics. But they convert into each other as the wave vector becomes complex. So this collision of singularities is what determines the convergence of the hydrodynamic expansion. This is what gives the critical wavelengths for the sound wave. But there is more to complex momentum. Okay, so I cannot resist mentioning this. This is not my work. But I still want to mention this very briefly. So there's a relationship, there seems to be a relationship between complex momentum and chaos. So chaos is, what is chaos? Basically, different people mean different things when they talk about chaos. Chaos is how microscopics gives rise to macroscopics. And in classical mechanics, one way to characterize chaos is through the so-called Laplace exponent, which tells about the divergence of trajectories of your system in phase space. So delta x is the phase space difference between your trajectories. And if that increases exponentially with some exponent lambda, lambda is this what people call the Laplace exponent. you can argue that there exists a quantum mechanical analog for the Lyapunov exponent, and it comes from taking the expectation value of the square of the commutator of two operators at two different times. So if that grows exponentially, you can argue that this lambda should be thought as the quantum analog of the Lyapunov exponent. Now, you can do like a very naive and stupid thing. Okay, you can just take a plane wave, and in this plane wave, such as something that has nothing to do with chaos, something that only has to do with fluid dynamics, you can take omega to be I times some real number, and you take k to be I times that real number over some velocity. You stick them into the plane wave, and you get something that increases exponentially. Now you say, okay, it's just a silly substitution. There is nothing to it. Now, what you want to do, you want to compare this with that. And it turns out that in many examples that you can solve exactly, the dispersion relation of the sound wave at complex momentum passes through the point that is exactly equal to this Lyapunov exponent that you can evaluate independently. Okay, so it seems to be that sound waves know about the Lyapunov exponent if you take momentum or the wave vector to be complex. There's lots of literature on that, so I'll not talk about that, but you can take a look at these papers if you're interested. So the bottom line is this: in many solvable examples, classical macroscopic excitations and non-classical microscopic excitations, they're merely different branches of the same multi-valued complex function. And also in many solvable examples, classical hydrodynamics at complex momentum seems to know about the quantum Lyapunov exponent. Now, my final story is this, okay? Why everything I said so far is wrong. So let's take a second look at the limitations of hydrodynamics. We know that macroscopic stuff is made out of microscopic stuff. In a quantum vacuum, we know that virtual particles are constantly produced and absorbed due to quantum fluctuations. Similarly, in a macro state, virtual sound waves are constantly produced and absorbed due to statistical fluctuations. These sound waves will backreact on the macroscopic physics because hydrodynamics is nonlinear and waves do interact. So what I have here is a cartoon when I have a solution to my classical hydrodynamic equation. This is the thick blue line, and I have a statistical fluctuation here. And there are some sound waves shown by these thin lines that are generated by the statistical fluctuations. And because of the nonlinearities of fluid mechanics, these waves are going to interact. And so what you thought was your solution to classical Navistox equation, that is going to change. So this is this back reaction. So is this back reaction relevant? Okay. Now, of course, in quantum mechanics, the back reaction is very, very important. The back reaction of quantum fluctuation is, in fact, responsible for most of the mass of the matter we see in the universe. This is reflected in the Nobel Prize in 2004 to Gross, Politz, and Wilczek. Now, the back reaction of statistical fluctuations is usually not so dramatic, but it does modify the Navier-Stokes equations near liquid-gas critical points and in 2 dimensions. Should you care? Well, it depends on the questions that you ask. So hydrodynamics to microscopic physics is like classical mechanics to quantum mechanics. So if you look at correlations, then classical versus quantum predictions, they can differ dramatically. Similarly, if you are interested in macroscopic long-time, long-distance correlations, then classical hydrodynamic equations, which ignore the back reaction, can lead to dramatically wrong predictions. Okay, this was in fact discovered many years ago in the first days of molecular dynamics in simulations of, in fact, billiard balls in early 1970s. So what does this mean? So this means that if you want to understand macroscopic correlations, such as velocity correlations or energy correlations in your fluid, hydrodynamics, the same as differential equations, not going to work. Power series like that, not going to work. The relationship between hydrodynamics and quantum Lyapunov exponents, probably not going to work. The fact that transport coefficients such as the viscosity or the electrical conductivity will determine for you the long distance correlations, that is not necessarily going to work. And that incompleteness of hydrodynamics has been well known in statistical physics for many years, going back to 1970s. So let me give you a simple example of viscosity. So this will only take 2 minutes, so we'll finish maybe in 3 minutes, if that's okay. So viscosity is something that tells you about the transfer of momentum between layers of a fluid. So what you're looking at here, you're looking at a picture of a fluid that is moving from right to left. So these yellow arrows indicate for you the velocity of the fluid. The fluid moves quickly on the bottom. It moves slowly on top. The thin blue lines indicate particles that jump between different layers of the fluid. And as they jump, say, from the bottom layer here to the top layer here, these particles can transfer momentum. Okay, so say a particle jumps from the fast layer to the slow layer, it can speed up the slow layer and transfer momentum. So this is what is measured by the viscosity. So viscosity is the way you describe this quantitatively. Viscosity is related to stress, in this example, Txy, and it's the proportionality coefficient between Txy and the y derivative of the x component of the velocity. And if you look at this example, then you see that the farther these particles jump, the more efficiently they can transfer momentum. And so if you work it out, turns out that in a gas, viscosity is proportional to this mean free path, which is roughly the mean distance by which these particles jump. And there are some proportionality coefficients, the mean thermal velocity or the density of your gas. Okay, so this I probably will skip in view of time. But what I want to show is this. In the previous picture, I had particles, but momentum can also be transferred by collective excitations. So these collective excitations are sound waves. I can have exactly the same picture where sound waves that are excited statistically jump between different layers of my fluid. And the mean free path for the sound wave is inversely proportional to the viscosity and the wave vector squared. Because remember, longer sound waves propagate, longer wavelengths, waves, they propagate for longer distances. If you now want to sum over all of those contributions of the sound waves, that is, you sum over all the possible momenta, you will find interesting things. You will find that the correction to viscosity is in fact inversely proportional to the viscosity itself. This means that if you want to take the viscosity to 0, it's a very, very singular limit. Another thing that you will notice is that if you only have 2 spatial dimensions, this integral diverges. It diverges at small wave vector. So it's an infrared divergence. And infrared divergence means long distance physics may be modified. So this tells you these effects are important in 2 dimensions. So I will not talk about how you describe such effects. I will just say that there's a modern way to describe these effects by converting hydrodynamics into a quantum field theory, something very similar to what you see in the standard model of particle physics. You will need to talk about symmetries. You will need to talk about Euler-Lagrange equations, which are actually the same as the conservation laws. That's slightly different from normal classical mechanics. You will need to talk about time that runs forward and backward and so on. Anyway, this is some technical details. All I want to say is that the techniques that you learn in field theory for the standard model of particle physics, they are directly transferable to describe these effects here. So where does this leave us? So for many years, I had a dream of a grand unified theory of hydrodynamics that applies to many different kinds of fluids. It ensures that the equations are sensible in the sense as I talked about at the beginning of the talk. It allows for systematic improvements. It correctly predicts macroscopic correlations, that is, those effects of the back reaction. It connects with quantum chaos, and most importantly is experimentally verified. So it looks that this vision of a grand unified theory of hydrodynamics is getting close to becoming true. It requires developing new kinds of field theories. These are so-called Schwinger-Keldysh field theories that I briefly mentioned here. And if I want to be optimistic, I want to think about it as another wave of quantum field theoretic methods for macroscopic physics. So I want to end with an encouragement. So as a student, one often tends to think that all interesting questions in physics, they have already been answered many years ago by the great. Okay, so hydrodynamics is an ancient field by modern standards, and people are still trying to figure out some very basic questions. So if as a student, you work in a field that is less than 200 years old, do not lose hope. There are surely many fundamental things left for you to discover. So I'll end here. Thank you very much for listening. Thanks.
Thank you so much for the very interesting talks. I think we have time for questions or comments. If you have questions, you can raise hand, one of these Zoom features, and then I can sort of allow you to unmute yourself. Okay, so while people are coming up to questions, I have one question. Oh, wait, Alexei has a question, so I allow him to speak. Yes, please, Alexei.
Thank you. What is the pathology with the relativistic hydrodynamics equation? Is it only when the gradients are large and there is some change on small time scales and spatial scales, or there is something more dramatic?
No, you're right. So what happens is that these pathologies, that technically speaking, you're absolutely correct. They technically speaking happens. The technically speaking happen for short wavelength modes and short timescale modes. However, it's a problem that you cannot ignore because the situation with solving classical equations is different from the situation, say, in field theory when you compute amplitudes. If you want to evolve the equation, if you actually want to literally to evolve the equation, you need to make sure that the mathematical problem is well posed. In other words, the equation does admit a well-defined initial value formulation. The equation is hyperbolic. Those equations are not hyperbolic. Now, on the other hand, you can think about this problem of instability. So I said thermal equilibrium does not exist. This technically speaking means that if you just look at a state where the fluid just sits there doing nothing at all, the infinitesimal perturbations of that fluid, they will grow exponentially. You're completely right that the instability happens due to the modes that are outside of the validity regime of the theory, of the low energy theory that you want to study. But the instability is real. If you want to actually solve the equation, you cannot ignore it. This instability will prevent you from actually doing anything useful with that equation. And so that's the difference between doing something in actually solving for the time-dependent classical evolution and looking at amplitudes where you can focus, focus at the origin of the frequency and momentum space.
So it seems this problem is similar to the problem of numerical instability on a grid. And if you set your grid spacing equal to the mean free path, then you'll have both problems, and maybe they can be solved using some numeric trick, or maybe not.
Maybe. So, however, it's important that the physics that you want to describe is the physics of viscosity. right? So you can set your perfect fluid on a grid, for example, and then you will have some numerical viscosity that just emerges because of the grid. But that's not what you want to do. You want to, if you want to describe a fluid whose viscosity is not just a numerical artifact, but the actual physical viscosity that is calculable and that is measurable, it does not become a problem of numerics. It actually becomes a problem of having equations that are mathematically well posed, because you do want to have viscosity as an input parameter into those equations. So it's the problem that has been around. Since early days, and so this is the comment that I made, that other exotic theories have been proposed in the 1970s to replace the Navistox. So those exotic theories, they do the same, they do a very similar thing. So they introduce like lots of short distance degrees of freedom. It's like Pauli-Villar's regulator. So you introduce extra UV degrees of freedom, and you engineer those UV degrees of freedom in such a way as to cure those problems with stability and causality. But I want to emphasize that the equations, they're not strongly hyperbolic, they're not even hyperbolic if you don't do the things that I talked about in the talk. So it's not just a problem of numerics. It's a problem of how to do it, and it actually touches on this question, to which I do not have a good answer yet.
I see. Thank you.
Okay, Jesse, do you have a question? I'm not sure whether you're raising hands or not, but let me unmute you. You can, if you have a question, you can ask. Oh, probably, okay, I'm not sure. Is there anybody else who have questions? So I have very short questions. So you briefly said that one of the difficulty, oh, somebody actually, there's a Q&A. Let's see. So, so Gabrielle, do you want to ask a question yourself? I'm unmuting you.
There. Hello. Hi. Thanks for the awesome talk. I was wondering whether there was an analogy to be made to a wick rotation. This obviously betraying great ignorance in my asking, but when you do the superficial operation of identifying, like substituting a imaginary wave vector into your solution, like, is there an analogy to be made structurally or tactically to what happens when you map the Schrodinger equation and the diffusion equation by an imaginary time?
Yeah, it's a good question. I don't see an immediate relation, just because the wick rotation is something that in the context of thermal field theory. So the wick rotation is something that allows you to talk about Euclidean physics. So the Matsubara formalism, for example, is something that would allow you to ask Euclidean questions. Now, the analytic continuation from Euclidean frequencies to real frequencies is actually a very, very subtle matter, and this is why, for example, numerical methods that exist in the Euclidean domain, such as lattice QCD, they do not allow you to calculate real-time phenomena such as the viscosity. So viscosity is like real time. So you want real time, you want finite temperature, and you want complex momentum and frequency at the same time. So so it's sort of similar to the wick rotation, but the way I normally think of the wick rotation is Euclidean physics as opposed to real-time physics, but this is actually real time, so it's very non-Euclidean, so to say. So unfortunately, I don't have a good intuition for that.
Thanks so much.
Okay, I'll take two more questions. So the first is from John Brady.
Yes, hi. Very nice talk. I enjoyed it very much.
Yeah, thanks.
I have a question about instead of doing a gradient expansion, one often makes a non-local expression for these properties. Is that equivalent to what you've done, or does it make any difference?
No, what I have done is still local. And the reason why I do this is I want to connect with viscosity, which is a piece in the first, which is the contribution to the first local term. So I'm not introducing any non-locality here in either space or time. So it's still everything is local. So the way I actually want to think about it, I really want to think in my head using an analogy with field theory, where you need to formulate theory with a short distance cutoff, and the short distance cutoff has to be such that it respects the symmetries of the theory. So not just the symmetries in language of field theory, it has to respect unitarity, and here it has to respect causality. So what I'm trying to do here, I'm trying to implement essentially a high derivative regularization in a way that does not require introducing any extra degrees of freedom and is consistent with causality in a macroscopic thermal system. Because lots of these problems come because you don't have a near vacuum excitation, you have a thermal excitation. But everything is local. I'm not introducing non-localities here.
Thank you.
Okay, so the last question from Lexi.
I wanted to ask, so there has been a lot of recent development in studying how quantum many-body systems approach equilibrium, quantum many-body thermalization, eigenstate thermalization hypothesis, its dynamical versions, and also emergence of hydrodynamics in these settings. So these are settings, of course, non-relativistic quantum mechanics, but where there are things like Lieb-Robinson bounds in which set the limit on the propagation of information. So if there is connections with what you described and kind of how these developments relate to each other and how one can
right. Thank you. Yes. Yes, so the things that you mentioned, so you mentioned they were done in the context of non-relativistic physics. I don't think there will be any difference when these things are translated to relativistic physics. So all the things that, all the progress that people have done using thermalization, approaching thermalization, I think that should go the same for relativistic physics. So what the system that I have been describing here, like in these examples of level cross and whatnot, these are very simple systems. I think they're so simple. I mean, they do have interesting phenomena like that on one hand, but on the other hand, they're so simple that they throw away a lot of that interest in physics of the type that you are talking about. So these are systems that are large n systems, and these are systems in which the limit of infinite n is taken before everything else. Okay, so you take n to infinity first, and you keep it infinity, and then you look at what happens near the hydrodynamic limit. So you actually, if you want to really, really understand what happens to thermalization, you want to take a slightly different limit. You want to take n finite, like maybe large, but finite. And then you want to take hydrodynamic limit first and see what happens. So I think what systems I talked about here, they're kind of too elementary, so to say. They still have this very nice phenomena, but yeah, they're not rich enough.
Okay, thank you.
Okay, so I'm sure there are more questions, but we are going to keep this session open for a while. So if any of you wants to ask questions informally, you can stay on. I think Kobe can help moving people to panelists if people wants to stay.
Yeah, if you'd like to stay, just raise your hand and we'll promote you to a panelist.
Good, yeah, so okay, so let's do that. And then, but for now, let's thank Pavel for the beautiful talk. Thank you so much.
Yeah, thanks.